Hello and welcome to the channel. This is going to be a series on building out the PETS algorithm, or probabilistic ensembles with trajectory sampling. The PETS algorithm is a model-based algorithm that is two parts. We're going to build a series of world models that are trained to take a state and an action and predict the next state and the reward. So, and then an agent is going to take a series of random walks through different action sequences, pick the best one based on the predicted return of the world model. So let's talk for just a minute about what it even means for something to be model based. Because if you're used to things like Q-learning is which is probably the first thing you've worked on if you're doing anything with reinforcement learning. It is effectively taking a state in from the environment. So a state could be a picture of the environment. It could be a map of what's going on in the environment. And it's going to attempt to predict the right action in that state. Model-based algorithms are a little bit different. So a model-based algorithm is going to try to build a model that predicts something about how the world works. It's going to build a model of the world. Again, that's why it's called model-based. And what that allows the agent to do is it allows it to imagine what might happen in a given scenario. So in PETS, the agent is going to learn to map a state and what action was taken to the next state it should expect based on that action. So if we're talking about the Lunar Lander environment, which is what we're going to be doing, and it sees that the last action was to fire the thrusters, maybe the agent should predict that the next state is going to be the Lunar Lander being a little bit higher. And it should predict the expected reward from that Lunar Lander being a little bit higher. So at that point, what we're doing is less directly model driven in the sense of it's not a model making the decision directly. What we're going to do is, with the PETS algorithm, is we're actually going to have several models that will predict the next state. So just breaking down, what's in the name, what does PETS mean? So a probabilistic ensemble. That's a fancy way to say that we're going to have several models trying to predict what's going to happen. So we're going to have 3, 4, 5 models that all take the state and all try to predict what the next state and reward are going to be based on the previous state and the action. We'll use a little bit of a simplified version of this approach. It will not strictly adhere to the paper, but it should get the general feeling of what this is supposed to accomplish. And then we're going to do something called trajectory sampling, which again sounds complicated. All this means is that we're going to randomly pick a number of different action sequences that the agent could take. So we might predict 100 different action sequences and then run them through the ensemble of models. And what that's going to let us do is we're actually going to be able to predict what will happen in each of those scenarios. And it won't be perfect, right? It's guessing. It's trying to think ahead. If I take these 50 steps, what will happen? And then whatever the best rewarded thing was in those steps, we're going to take the next couple of steps along that path. So if we've predicted 50 steps down the line and we go, hey, this looks like the best route, then we're going to take the next couple of steps and we're going to try, and then we're going to go through and calculate again. This ends up being pretty accurate. We're not waiting on one model, or we're not assuming one model has to decide what's going to happen. And we have the advantage of being able to try out many different things. We have many models trying to make a prediction. So it ends up being pretty accurate for the things that it does. But Where it falls apart or where it has issues is in resource utilization. So this is one of the only things I've built out where the first time I ran through it, I actually had the environment running slower than human visible. And what I mean is when I ran the environment, it was not able to move as fast as a human playing. And if you've done reinforcement learning before, most of the time you have to slow down the environment so that you can see what's happening. Otherwise, it's just rocketing through it. But this is because it's predicting many different trajectories, and then every few steps it's testing those trajectories against its own world model. It is actually very computationally expensive. So that is something to be aware of with pets. It is a computationally expensive algorithm, but it does tend to work well in scenarios where you have a numerical state. So we're not going to be working with images. We're going to be working with a numerical state. And then we are going to be, working in an environment with a series of numerical outputs. It's not just taking, a left or a right. It's going to be outputting different degrees of thrust. Things to know going into this. I'm an AI enthusiast. I'm not a researcher. Some things may not be perfect. I do this on my own time. This is a coding walkthrough of a project that I've built. It's not a complete course. You're not going to learn everything about model-based reinforcement learning. Hopefully you'll learn a few things and you'll have fun going through the project. If you need help, you are welcome to post in the video description. Engagement helps the channel. And you are welcome to go jump on Discord. I will have a link in the video description. And if you're new here, check out my other videos. I talk about robots, reinforcement learning, and sometimes I get into some fun security and general programming stuff. So with that, I'm going to say, let's go ahead in the next video and get started on the project. See you there.